Welcome to the National Institutes of Health, Office of Intramural Training and Education's webinar on Laboratory Math 1, Exponents, Units, and Scientific Notation. This webinar is intended to review some basic math skills that are commonly used in biomedical research. Even if you have a strong mathematic background, it may serve as a good refresher. The first question to address is simply, what is lab math? Lab math is any math skill or technique that is used in laboratory science. It can range from basic math skills to complex calculus and trigonometry. In this webinar, we will review the basic math skills you will need to understand to perform many of the calculations common to biomedical research. Because much of scientific research is performed on either microscales or macroscales, we will cover multiplication and division with exponents, focusing on working with the powers of 10. We will discuss scientific notation and how its use can simplify calculations and the presentation of data. We will also introduce the mathematics of the metric system, cover the common nomenclature, and demonstrate how to convert the units within the system. In a future webinar, we will discuss making solutions and dilutions in the lab. Before we can discuss how to multiply and divide exponents, it is best to define what an exponent is and cover a couple of the basic rules. Simply defined, an exponent is a shorthand notation for the number of times a number is multiplied by itself. For example, n to the fourth power is shorthand for n times n times n times n, or n times itself 4 times. N to the second power, or n squared, is equal to n times n, or n times itself twice. Exponents can also be negative numbers. Negative exponents are shorthand notation for the inverse of the corresponding positive exponents. Therefore, n to the negative fourth is equal to 1 divided by n to the fourth. This extrapolates out to be 1 divided by n times itself 4 times. By rule then, n to the first is just n. Conversely, anytime you see a number, in this case denoted by the letter n, it can be written in an exponent as n to the first power. Also, that any number to the 0 power is equal to 1, so n to the 0 power is 1. Conversely, you can denote 1 as any number to the 0 power. As mentioned earlier, much of biomedical research is performed on micro and macro scales. These numbers can be long and cumbersome, both to denote and to work with. To help simplify these numbers and make them more workable, many numbers in a research setting are written as a power of 10. As with all exponents, in powers of 10, the exponent is equal to the number of times that 10 is multiplied by itself. However, the base number 10 is easy to work with, as the exponent is also equal to the number of places to the right of the 1 that you place the decimal point. Said another way, the exponent is equal to the number of zeros between the 1 and the decimal place. In 10 to the 0 power, there are no zeros between the 1 and the decimal point. In 10 to the power of 1, there is 1 zero between the 1 and the decimal point. The same is true with 10 to the second power, or 10 squared. It is equal to 10 times 10, which is 100. And in 100, there are 2 zeros between the 1 and the decimal point. As you start to get to larger and larger numbers, you can more easily understand why using the shorthand exponent is so appealing. It is easier to work with 10 to the 6th power than to write out the 1 and the 6 zeros between the 1 and the decimal point. Just as powers of 10 can be used as shorthand for very large numbers, they can also be used as shorthand for very small numbers that use up a lot of space when written out. We mentioned earlier that negative exponents are equal to the inverse of the corresponding positive exponents. So for powers of 10, a negative exponent is equal to the number of spaces to the left of the 1 that you place the decimal point. So for 10 to the negative first power, you will move the decimal point 1 place to the left of the 1, and your answer will be 0.1, or 1/10. 10 to the negative second power would be equal to 1 divided by 10 to the second power, or 1 divided by 100, also called 1/100ths, and written 0.01. Notice the decimal point is 2 places to the left of the 1. As a general rule, it is best to use a leading 0 when writing a number less than 1. That is, there should be a 0 to the left of the decimal place to indicate that the number is less than 1, because the decimal point may be hard to see. Again, when you start to work with very small numbers, such as 1/1,000,000th, it is beneficial to use the shorthand of 10 to the negative 6th power. Any number can be written as a power of 10. As we will discuss in future slides, this becomes a powerful tool for simplifying the calculations that are needed for lab math. To write a number as a power of 10, it is easiest to start with the number itself and write it with a decimal place present even if 1 isn't there already. So 3 is written 3.0. The next step would be to determine how many places you need to move your decimal point such that only one integer remains to the left of the decimal point, in this case 0. The number of places you have to move your decimal point then becomes the exponent on the 10. Remember that 10 to the 0 power is equal to 1. Since any number multiplied by 1 is equal to the number itself, we can write the number 3 as 3.0 times 10 to the 0 power. For a number like 30, we write the number 30.0. Then we move the decimal point to the left one place. 1 then becomes the exponent of the 10. So we can write 30 as 3.0 times 10 to the first power. 300 is first written 300.0. We move the decimal point to the left 2 places, and 300 can now be written as 3.0 times 10 to the second power. You can use the same principle for writing numbers less than 1 as well. The only difference is you'll be moving the decimal place to the right, and the number of places you move the decimal point becomes the negative exponent of the 10. For example, 0.004. We will move the decimal point 3 places to the right to get 4.0. Therefore, the exponent of the 10 will be negative 3, and 0.004 can be written as 4.0 times 10 to the negative third power. Take some time to work out the rest of the examples. Now, check your answers. If you got them right, great, good job. If not, try reviewing this slide again. If you are having trouble understanding the purpose of writing numbers in powers of 10, take for example one of the most famous numbers in science. Avogadro's number for defining the number of molecules in a mole of any substance is 6.0225 times 10 to the 23rd power. That is a lot of zeros to write out if you don't use shorthand to do it. Partly for this reason, writing numbers as powers of 10 is called scientific notation. Scientific notation is a method of writing numbers in terms of decimal numbers between 1 and 9 multiplied by a power of 10. It dictates that there is exactly one placeholder to the left of the decimal point, an integer between 1 and 9. The rest of the number is written after the decimal point and then multiplied by the appropriate power of 10. This is most easily explained by looking at examples of numbers written in scientific notation. The number 1.25 is easy to translate into scientific notation. It already meets many of the criteria. There is one placeholder to the left of the decimal point, in this case, the integer 1. To convert it to scientific notation, we just have to multiply it by the appropriate power of 10. Since we want the number to stay the same, we multiply by 1, which is 10 to the power of 0. As a note, you will almost never see 10 to the power of 0 written out unless it is being used in the arithmetic. So what about converting 25.78 into scientific notation? Can you do it? If you follow the rules and have only one placeholder to the left of the decimal point, it would mean moving the decimal point one place to the left. As we learned in the previous slide, that 1 becomes the exponent of the power of 10. So 25.78 is equal to 2.578 times 10 to the first power. Now, what about 100,410? Can you convert it to scientific notation? Did you come up with 1.0041 times 10 to the fifth? If so, good job. If not, try reviewing the criteria for scientific notation, and then review the principles from the previous slide. One last note about scientific notation. When writing a number in scientific notation, you only record significant digits, which raises the question, what is a significant digit? A significant digit is any digit within a number that contributes to the precision of the number. More simply put, all digits are significant except for placeholders. Again, the easiest way to understand what significant digits are is by example. So, if any digit in a number other than placeholder zeros is a significant digit, what is a placeholder 0? Basically, any zero or series of zeros that are not between two integers. So in the number 0.0005, all the zeros are placeholders. So which zeros are placeholders in the number 35,000? All of them. Now, is a 0 in the number 1054 a placeholder? No, it is not, because there are integers on either side of it. Therefore, that 0 is significant. Another way to gauge whether a digit is significant is to determine if you would report it in the scientific notation. Placeholder zeros of a number are represented by the powers of 10 in the scientific notation. Therefore, any 0 that you would not report in the scientific notation is a placeholder, and thus is not significant. An important rule when multiplying and dividing numbers is to remember that your result should have as many significant digits as the measured number with the fewest significant digits. So if you multiply a number with 2 significant digits by a number with 7 significant digits, your result will have only 2 significant digits. Let's go through a few examples and determine the significant digits of some numbers. The number 2500 has 2 significant digits. The 2 and the 5 are both significant. The 2 zeros are both placeholders. This makes them not significant. What about the number 0.0000654? How many significant digits are there, and which digits are they? There are 3 significant digits. The 6, the 5, and the 4 are all significant. Again, in this example, the zeros are all placeholders. As practice, how would you write this number in scientific notation? It would be 6.54 times 10 to the negative 6. Now, how many significant digits are in the number 1045.01? All 6 of the digits are significant, as none of the zeros are placeholders. Again, if you were to write this number in scientific notation, you would use all the digits. It would be 1.04501 times 10 to the third. Now we are going to look at how to perform calculations with powers of 10. When multiplying powers of 10, you add the exponents together, and the result is 10 to the sum of the individual exponents. Let's look at a few examples. We multiply 10 to the second power by 10 to the third power by adding the exponents 2 and 3 and keeping the base 10. This yields us 10 to the fifth power. As a matter of checking the math, we can use the full written out numbers of 100, 10 to the second power, times 1000, 10 to the third power, which is equal to 100,000, same as 10 to the fifth power. Now, what would be the result of multiplying 10 to the fifth power and 10 to the fourth power? Following the rule of adding the exponents, we would get 10 to the power of 5 plus 4, or 10 to the ninth power. The principle is the same for negative exponents. 10 to the negative 4 times 10 to the third is equal to 10 to the sum of negative 4 and 3, which is negative 1. So what about 10 to the fifth times 10 to the negative 2? Did you come up with 10 to the third power? Feel free to check these using your calculator. Logically, division is the opposite of multiplication. Practically speaking, when dividing powers of 10, it is the opposite of multiplying powers of 10. That is, when dividing powers of 10, you subtract the denominator exponent from the numerator exponent to reach the result. Again, let's look at a few examples to understand how this works. We divide 10 to the fifth power by 10 to the third power by subtracting the exponents 3 from 5 and keeping the base 10. This yields us 10 to the second power. Now, what would be the result of dividing 10 to the seventh power by 10 to the ninth power? Following the rule of subtracting the exponents, we would get 10 to the power of 7 minus 9, or 10 to the negative second power. Another tool for dividing powers of 10 is to realize that dividing by a power of 10 is the same as multiplying by the negative of the bottom exponent. That is basically saying that the 1 over 10 to the ninth is equal to 10 to the negative ninth. So by basic mathematical principles, 10 to the 7th divided by 10 to the 9th is equal to 10 to the 7th multiplied by 1 over 10 to the 9th. This is then equal to 10 to the 7th times 10 to the negative 9th. Knowing that we can multiply powers of 10 by adding their exponents, we get 10 to the 7 plus negative 9, or 10 to the negative 2nd power. Now, using this technique, can you divide 10 to the 3rd by 10 to the 13th power? This is equal to 10 to the 3rd multiplied by 10 to the negative 13th, which is equal to 10 to the power of 3 plus negative 13, or 10 to the negative 10th power. Now that we understand how to work with the powers of 10 on their own, we need to learn how to work with numbers in scientific notation. That is, a base number times a power of 10. The first rule to know when adding or subtracting numbers in scientific notation is that the numbers must be in the same power of 10. We will discuss examples of this in the next slide, but two basic steps must be taken when adding or subtracting numbers in scientific notation. First, convert the smaller number into the same power of 10 as the larger number. Remember the rules of moving the decimal place and adding to or subtracting from the exponent. Once in the same power of 10, add or subtract the root numbers while leaving the result in the same power of 10 as the numbers being added or subtracted. To multiply and divide numbers in scientific notation, you multiply and divide both the root numbers and the powers of 10. So when multiplying, you would multiply the root numbers and add the exponents together. When dividing, you would divide the root numbers and subtract the exponents. We will cover examples of this in a later slide. As stated in the previous slide, to add or subtract numbers in scientific notation, the numbers must be in the same power of 10. Once in the same power of 10, you simply add the root numbers together. So, let's look at a few examples. Consider 3.5 times 10 to the 3rd plus 4.0 times 10 to the 4th. The first thing we need to do is convert the smaller number, 3.5 times 10 to the 3rd, into a number with the power of 10 to the 4th. Since we would be adding 1 to the exponent, we would then move the decimal place to the left. So our problem would now read 0.35 times 10 to the 4th plus 4.0 times 10 to the 4th. Now we just add the root numbers 4.0 and 0.35 together, and we get 4.35 times 10 to the 4th. Now see if you understand the principles of adding numbers in scientific notation by working out this problem. 5.11 times 10 to the 5th plus 6.5 times 10 to the 2nd. First, convert the smaller number, 6.5 times 10 to the 2nd, to a power of 10 to the 5th. Since you will be adding 3 to the exponent, it means you move the decimal point 3 places to the left, and it gives you 0.0065 times 10 to the 5th. Now, you just add the two root numbers together to get 5.1165 times 10 to the 5th power. Multiplication and division of numbers in scientific notation is a little more straightforward than addition and subtraction. There is no need to convert the numbers to the same power of 10. To multiply or divide powers of 10, you treat the root numbers and the powers of 10 individually. Let's start with multiplication. First, you multiply the root numbers together, and then you multiply the base 10 powers, which means you add the exponents. Again, let's go through a few examples. 2 times 10 to the 4th multiplied by 4 times 10 to the 3rd. Start by multiplying the root numbers 2 and 4. Then multiply the powers of 10 by adding the exponents 4 and 3. This gives you a result of 8 times 10 to the 7th power. Now, you work out 5 times 10 to the negative 3rd multiplied by 2 times 10 to the 5th. Did you start by multiplying the root numbers 5 and 2 together? Then, did you multiply the powers of 10 by adding the exponents? Hopefully, you also remember to write your answer in scientific notation by moving the decimal place to the left one place and adding 1 to the exponent to give the final answer of 1.0 times 10 to the third power. Now, work through 1.25 times 10 to the fourth multiplied by 3.5 times 10 to the sixth. Remember what you have learned about significant digits when reporting your answer. Did you end up reporting 4.4 times 10 to the 10th power? Remember that you only report as many significant digits as the measured number with the fewest significant digits. In this case, 3.5 times 10 to the 6th only has 2 significant digits, and thus your result can only have 2 significant digits. Having come this far in the webinar, you may be asking why these basic math skills are considered laboratory math. The answer is they are all required for working within the metric system, and all scientific measurements are made using the metric system. So what is the metric system? It is a decimal system of weights and measures. Since there has been a large focus on the powers of 10, it will probably not surprise you that decimal means pertaining to powers of 10. In the next few slides, we will introduce the units of the metric system and how the powers of 10 make it easier to work with the scientific measurements. First, it is important to know the base units for each measurement. The name metric is derived from the unit of measure for length, the meter. The unit of measurement for mass is the gram. For volume, it is the liter. For time, it is the second. And the unit of measure for the amount or total number of something is the mole. Knowing how to work within the metric system requires knowing the terminology, understanding what each term means, and appreciating how they relate to one another. We are going to use length in our discussion of how the metric system works, but the same approach would apply to mass, or volume, or any other unit. The base unit for any measurement is 1 times 10 to the 0 power, or 1. 1 meter is the base unit for a measure of length and can be written 1 times 10 to the 0 meters. The commonly used prefixes in the metric system refer to increases or decreases in value by 1,000, or 10 to the third power. Kilo means 1,000. Thus, 1 kilometer is equal to 1,000 meters, or 1 times 10 to the third meters. Milli means 1 1,000th. Thus, 1 millimeter is equal to 1 1,000th of a meter, or 1 times 10 to the negative third meters. These prefixes allow you to further use shorthand to limit your writing. It is easier to write 15 millimeters than to write out 1.5 times 10 to the negative 2 meters. It is important to note that because the common prefixes represent shifts of 1,000 or 10 to the third, that not all numbers will fall between 1 and 9. It is acceptable to write 15 millimeters as opposed to its scientific notation in the base unit. Now that we have worked through the process of converting up and down the metric scale, try and fill in the numbers associated with each prefix in the table. The first few are done for you. As you start to complete the table, you may notice a shortcut. To move from the base to kilo, you simply add 3 to the exponent and make it 1 times 10 to the third. The same can be done when moving to the smaller units. You simply subtract 3 from the exponent. To move from the base to milli, you would subtract 3 from the exponent and get 1 times 10 to the negative third power. Now to move up from kilo to mega, you add 3 more, and mega is equal to 1 times 10 to the 6th. The same is done to get 1 times 10 to the 9th for giga, and 1 times 10 to the 12th for tera. If you go from milli to micro, you subtract another 3. You see that micro is 1 times 10 to the negative 6. If you continue, you will have nano equal to 1 times 10 to the negative 9, and pico equal to 1 times 10 to the negative 12. These are merely the most common prefixes. There are many more for both larger and smaller numbers. Also, in some systems of measurement, additional prefixes are used to represent the numbers other than orders of 1,000. An example would be the centimeter, used to represent 1 100th of a meter, and 1 times 10 to the negative second meters. Something else that is important to note. If 1 nanometer is equal to 1 times 10 to the negative 9th meters, the inverse is true as well. This means that 1 meter is equal to 1 times 10 to the 9th nanometers. Logically, that makes sense. If a nanometer is much smaller than a meter, there should be a lot of nanometers in every meter. In fact, there are 1 times 10 to the 9th nanometers in every meter. Now that we know the terminology for prefixes within the metric system and to what numbers they correspond, let's look at how to convert between them mathematically. Specifically, let's calculate how many meters there are in the other units of length. A meter is the base unit, meaning 1 times 10 to the 0 power meters, or 1 meter. A kilometer is 1 times 10 to the 3rd meters. We could also say that there are 10 to the 3rd meters in a kilometer. We also know that a megameter is 1 times 10 to the 3rd kilometers, and thus there are 10 to the 3rd kilometers per megameter. To determine how many meters are in a megameter, you multiply 10 to the 3rd kilometers per megameter times 10 to the 3rd meters per kilometer. The kilometers will cancel out, and the exponents are added, and you get 1 times 10 to the 6 meters per megameter. We can use the same principles to work into the smaller units as well. We know that 1 millimeter is equal to 1 times 10 to the negative 3rd meters, or that there are 10 to the negative 3rd meters per millimeter. We also know that a micrometer is equal to 1 times 10 to the negative 3rd millimeters, or that there are 10 to the negative 3rd millimeters per micrometer. Based on what we learned in the last slide, can you then determine how many meters there are in a micrometer? If there are 10 to the negative 3rd millimeters per micrometer, and there are 10 to the negative 3rd meters per millimeter, if you multiply these together, the millimeters then cancel out, and you can add the exponents, again getting 10 to the negative 3 plus negative 3 meters per micrometers, or 10 to the negative 6 meters per micrometer. This principle is important when converting between units that do not start with the base unit. For example, 5 kilometers is equal to how many nanometers? We know that there are 10 to the 3rd meters per kilometer, and we also know that there are 10 to the 9th nanometers per meter. Therefore, we can first multiply 5 kilometers times 10 to the 3rd meters per kilometer, and then multiply 10 to the 9th nanometers per meter. The kilometers cancel out in the first multiplication step. The meters will cancel out in the second multiplication step, and we can solve that 5 kilometers is equal to 5 times 10 to the 12th nanometers. Now, try and work out how many kilometers are in 15 millimeters. The first step is to set up the equation. 15 millimeters is equal to how many kilometers? Now, write out what you know about each in terms of meters. There are 10 to the negative 3rd meters per millimeter, and there are 10 to the negative 3rd kilometers per meter. Thus, we can multiply 15 millimeters by 10 to the negative 3rd meters per millimeter, and then multiply that by 10 to the negative 3rd kilometers per meter. The millimeters cancel out in the first step, and the meters cancel out in step 2, and we are left with 15 times 10 to the negative 6 kilometers. Thank you for watching this webinar on Lab Math. We hope it has helped you understand the fundamental skills you will need to perform many of the calculations you will face in the research setting. For more training resources, please visit our website by clicking the link on this slide. Also, check back on that page in the near future for Lab Math 2, Solutions and Dilutions.